All right, let's go ahead and get started. The first thing has to do with assignment 1. There was certainly a lot of activity on Piazza yesterday and the previous day. So let's talk about assignment 1. Here's my plan. For the future, that is sort of starting with now, we don't use Clouderizer and we don't use Collaboratory because both of them have issues. Instead, we use Google Cloud Platform. Right? The only reason I had been loath to do that is I only had a $50 credit to give you. However, Google does offer a one-time $300 credit, which you should all be able to be eligible for. I think you have to provide billing for it, so you have to actually set up a credit card, I believe, but the first $300 is free, and you can set up budgets and stuff like that so that it doesn't hit you. So that's what I'm going to plan on. We'll standardize on Google Cloud Platform, and I'm working on creating a setup for that. So, yesterday I was trying to solve various problems. How many of you got hit with problems yesterday in using EE? Okay, quite a few. So, it was very unfortunate that yesterday someone committed a failing patch, right? It's like to Fast AI. That, it just couldn't have gone any worse, I think, than that. So at least I reported it, it's fixed, but that is unfortunate. So, however, it's also real life, right? Stuff like that happens, especially when you are installing from the head, of the branch. Now, on the other hand, that has good and bad parts to it as well, right? The good parts being you pick up any bug fixes. The bad parts, you pick up any new bugs too. I think what I'll do with this installation is just install to a particular commit ID so that it's sort of known good and we won't get anything more from here on out. But that way at least all of us will be on the same version, which is pretty important. So if there's any weirdnesses where someone's running a different version. So I'll do that. I'm working on a setup. So yeah, we had all these issues yesterday. I worked on that. I thought about it last night. So I got up at 2:30 this morning and said, okay, let me make a script that will set up our environment that we want on Google Cloud Platform, right, and Compute Engine. Here's what it's not quite there. It's really close. Like I can run my notebook and do some learning, but the output is looking a little funky, and I need to ensure that it works well from scratch. It's a one-time expensive setup, just like Clouderizer was, because it's got to go install a bunch of stuff. However, it's going to install it to your persistent disk, your 30 gig disk that you set up. And once it's installed, it doesn't ever need to be installed again. So from then on, the startup is on the order of 30 seconds or a minute. Okay, and you will be back to exactly where you were, other than the in-memory state, right? But all your disk will be contained. What that means is there'll be no Google Drive integration, right? I could theoretically go and try and install that, but that's even more work than I want, and that's part of why Clouderizer seemed like such a good idea. So if you need to upload or download, you have really about 3 options. You can use SCP, right, or Secure Shell. You can use Jupyter's upload and download capabilities. Right, so in the little Jupyter File Explorer, you can select a file and right-click and download it, and then it also has an upload button, so you can upload. So that'll work. And then a third thing you could do is you could do something like use the Kaggle CLI command line interface in order to install Kaggle datasets. So there'd be a little more manual work in the sense that if you want to install a dataset, you just don't go into Clouderizer and select the dataset. You need to actually run the Kaggle command line interface. As well, the setup requires a touch more work in Google Compute Engine. There's a firewall rule you have to set up and so on. And so I think what I'm going to do is require that you install the gcloud command line interface. So on your Mac, on your Windows machine, on your Linux machine, it exists for all 3 of those. But basically, you'll go in the terminal, and then you can just paste in a command to create this firewall rule, and then paste in another command to create your instance. So you don't actually have to go, open this dialog and change this and so on. All right? Questions so far? All right, I need volunteers. I would like volunteers this afternoon if anyone is available. I'm around sort of from 1 to 4. If anyone has time to help me bulletproof, I guess, the instructions and scripts. So is it more convenient to do that in a lab or in my office? And is there anyone who might be available? Maybe? My office then? Okay, that's great. So given these changes, we're postponing the deadline by 1 week. So it's no longer due tomorrow night, it's due a week from tomorrow night. And part of the reason, right, this assignment is basically a hello world. Right? Everyone familiar with hello world? Where did that come from? Where did it come from though first? Like where did it first appear in print? I heard something? The C programming language by Kernighan and Ritchie back in the late 70s, I guess. And so they had, the very first thing is they said, let's just print a hello world program, and then here's the way you compile it, and here's the way you execute it. And you think, that's kind of stupid, right? But why is it not stupid? Exactly. It proves everything's set up correctly, right? Half of the job is making it so you can compile and run hello world, right? In any language or any sort of environment and so on, right? For us, doing the dogs and cats is our hello world, okay? So you have like a hello world plus, which is actually doing not just dogs and cats, but dogs and dogs and dogs and dogs and dogs. So that's the reason for this, is to make sure it is all working so that for future assignments we actually do something interesting. Questions about assignment 1 then? Oh, there was one last thing, which is on Thursday I'm going to go over in class how to do it, how to use this new environment. Okay, what to do to set it up. Let's say Wednesday. Yeah. Any other questions? All right, so let's skip the nitty-gritty and the hello world problems. Oh, I know the other thing I was going to say about kind of running from head. And that is, right, I worked for Google a lot of years, and we had a very interesting setup there. I continue to have it, which is one giant repository for all of the code, which is, I guess, hundreds of millions of lines. It's a lot of code, okay? And so number one is all the source code is available. And that's kind of nice because you can go look at any source code except for a very small amount of code that they have sort of protected and on a need-to-know basis. But you can see it all, and you can also check in code anywhere. So if you find an error, including just like a documentation error, you can make a commit and propose that. There are code reviews, and whoever owns that area was going to review it and okay it. But that part's kind of nice. The other thing that's interesting about Google is everything gets built from head. Okay, so pretty much nothing gets released by version numbers, right? So you don't have a particular version of this library, Google library that you're using. Instead, you just use the latest, whatever's checked in. That is good and bad, right? The bad part is if you check in a change to something that's used widely, you can break a lot of people. And so the rule is, if you broke something, just revert that commit as soon as you can, and then spend your time going to fix it. Don't say, oh, I know what the problem is. I'll check in a fix to this, right? Because then you often are just making it worse. On the other hand, it's nice having the latest code, you know, the latest fixes and so on, but there's just a lot of responsibility of making sure you don't break things. And there's a lot of automated tests. FastAI clearly is missing some automated tests before check-in. All right, so we're going to talk now about the structure of our neural network. Okay, what a neural network is in a lot more detail, what an actual neuron is, how you compute the output given your inputs and your weights and your biases. On Wednesday, I was about to say Thursday, on Wednesday we will talk about how you actually do the training. Okay? That is, how do you update the weights? For now, we're going to just assume the weights exist. So let's look at what we got here. We've got a perceptron, and it's got, oops, three weights, and it's got a bias. Okay? So that is those are the parameters of the perceptron. And what happens basically was just do a weighted sum. So W1x1 plus W2x2 plus W3x3 plus B, and we look at the result. If it's positive, we'll output a 1. Otherwise, we'll output a 0. Okay, so these were the first versions of neuronic-like things. Perceptrons were big in the late 50s to mid 60s until there was an important book by Minsky and I think it's Papert called Perceptrons. And they basically showed that there are some problems that perceptrons aren't very good for. So if you have a single layer perceptron, doing something like calculating XOR is really hard. In the sense you can't do it locally, right? The goal, you'd think, is kind of to work locally on things, and the XOR problem is sort of inherently a global problem. So after that, work in perceptrons basically shut down until the late 70s, I guess, when a group at UCSD started working more on that. So perceptron, where will we use perceptrons? Whoops, I didn't. We'll never use perceptrons. Okay. And let me just sort of distinguish here. We're going to use the right-hand side, but we won't use the left-hand side. So we're going to do this weighted sum. We're going to add in the biases, and that's basically the weighted input. Okay. Instead, what we're going to do is use a more general version of the perceptron, which has a function here that's applied to the weighted sum. So for a perceptron, g of x equals, what does it look like? It's what? Yeah, so the indicator function is 1 when it's, is it greater than or equal to 1? Yeah, so. And if x is greater than 0. So that's how you would code up a perceptron, sort of as a more general neuron. So g is the activation function, and what comes out of here is the activation, which we'll often call A. And this value we'll often call Z. Okay. There are some common activation functions. ReLU, Sigmoid, 10H, Softmax, we'll talk about those. Okay. So, but let me back up a second. Does this part make sense? And then we're going to put these, we'll see, together into a larger network.
So does the activation function just compute one real value?
Yes. So the activation function is given a real value and computes a real value. So let's look at what's in reals. Let's see. So these are in the reals, or possibly integers, right? These are in reals. The output is in a real, which kind of makes sense because it's being used as an input to the next layer. So we want to have reals there. Other questions? All right, let's look at ReLU. So ReLU, which stands for rectified linear unit, is almost linear. We're going to see later on today that it is vital that G not be linear. Okay, we can't have a neural network that has all linear activation functions because that limits what we can compute. Okay, we'll look at that. So a rectified, so basically it's max of 0x. So this looks like when x is positive, it looks like this. And when x is negative, yeah, it's just a long 0. So is this linear? No, it's close. It's almost as close as you can be to being linear, but it is not linear. There are some nice things about this. Okay? If you assume for the sake of argument that the input to G is distributed evenly around 0, then half the time, what's this going to be outputting? 0. And half the time it's going to be outputting something. It might mean the same thing. So that tends to reduce the amount of non-zero activations that are coming out of a particular layer. And that turns out to be handy. Another really nice thing about this, what's the slope? Whoops. Right, the slope is 1. Here the slope is. And here, we'll say it's 0. So we'll define to be 0. So slope is 1 is nice. We're going to see with some other activation functions that sometimes what happens is the slope becomes very close to 0. And as we'll learn on Wednesday, the slope is what's going to basically help us learn. Okay, that's what we're going to be using to try and doing our minimizing, our hill. It's the opposite of hill climbing. Hill falling? Hill descent, thank you. Yeah, that's good. There are some slight alternatives to ReLU, but you'll find in practice this is used in virtually all hidden layers. And this is a change that's happened in the last 4 years, I would say. Okay, so they used to use what we'll see next, which is Sigmoid or TANH for most of the, and it just doesn't train as well. Okay, so a leaky ReLU says, getting ahead of ourselves, if the slope is 0, that means we're going to learn nothing over there. What that means is if we have a particular neuron which is going to output 0 because it has a ReLU, then we're not going to be able to make any changes to that weight because our slope there is going to be 0. So the derivative is 0. So when we try and figure out how we want to change our weights, we're not going to change them at all. So this means it's only going to be updating our weights for those neurons that are outputting something that's non-zero. It'd be nice if you could be able to do some sort of updating in the 0 case. And so a leaky ReLU trying to make that less than 1. So basically it's max of lambda x comma x, where lambda is between 0 and 1. Right? If it's 0, then we've got, and let's actually make this strictly less than 1. Because if it's equal to 1, what does that mean this function is? It's linear, and we just decided we don't want that. It's strictly less than 1. So you might make lambda be 0.1, 0.01, 0.0001, something very small, but just something so we get a little bit of slope there. Okay. Could be used, probably could replace all uses of ReLU. In practice, what do people use? ReLU. Questions about this? I know the slope isn't will make a lot more sense once we look on Wednesday, how we do this back propagation. So questions? All right, sigmoid. Sigmoid we actually have used already. So g of x is 1 over 1 plus e to the negative x. And it's often called the sigma function. What's its range? When x is large, what does it take on the value? 1, right? Because this becomes almost 0. So we're open interval from, and if x is very small, if x is very negative, I mean, then this becomes very large, and so this becomes 1 over a very large number, so it's 0. So let's look at, let's say here's 1, and we'll just throw in 1/2 right beneath it. And this looks like what you might call a sigmoid. Right, with 2 asymptotes. What happens to the slope if x is, I don't know, in sort of this range here? Like roughly, what's the slope? One, I mean, some reasonable number, right? It's not really small. Is it really small anywhere in this function? Yeah, right? Up here is really small, so it's close to 0. And here, it's really small. It's close to 0. And that is bad for learning. So basically what that means is if you've got a sigmoid neuron that is outputting something very close to 1, and it should be outputting something, let's say, more towards 0, it may take a lot of training to try and get it to move, because every step it's going to be moving based on the slope, and it's going to be slow and slow and slow and slow. That also kind of shows that extreme values of the inputs, right? So the reason we were very close to 1 is because our weighted inputs were very, very large. And so we can get to problems if our inputs become very large or very small. Either inputs are our initial inputs or inputs as we're going layer to layer to layer. And so for this reason, we don't use sigmoid much. So it used to be used in hidden layers. And it's not anymore. It's replaced with ReLU. Where would it be used? Where does this output range really nice?
The final layer.
Final layer for what? What kind of classification? Binary classification. So this is great for the last layer in binary classification. And this is exactly what's used. So what will be happening in learning, the learning is going to try and drive up the sum of the weighted inputs for positive examples and drive down the sum of the weighted inputs towards, big negative numbers for negative examples. Questions on this? All right. We have the tan h. So if sigma x is 1 over 1 plus e to the negative x, then g of x, which is tan h, is 2 sigma 2x minus 1. Let's figure out first what's the range. What's sigma x's range? 0 to 1. So 2, 0 to 1 is 0 to 2 minus 1 is negative 1 to 1. right? And so basically, it's just a scaled, it's not a very good picture. Let's see. And I'm very careful not to show any scale here so that my scaling can't be wrong, right? Because we could just define whatever axes we need to make this work. Okay, so the range is -1 to 1. And sometimes it can be useful to have this range. This also was used a lot in hidden layers. The nice thing about the tan-H is that it's producing negative and positive numbers, right? So basically, we're sort of centered around 0, and that can be a very good thing for training. So the sigmoid often would be replaced with a tan-H because the sigmoid was pushing stuff, to become positive. So we're losing out on getting negative outputs. But you don't really need to know about tan-H because we'll probably never be using it in this class, and you probably will never use it. So we'd be using ReLU for internal ones. You could try leaky ReLU because you might get slightly better results. And we'll use sigmoid as our output. And sigmoid's great for binary classification. It's also good for multi-class classification. So let's go back to that. So this is where we can have 0 or more classes for a given input, right? So it's an image that contains a man and a woman and a dog and a cat. So if we had those 4 classes, a man, woman, dog, and cat, what would we want our output layer to look like? Say it again. Why would we want them to sum to 1? So it's not man or woman or dog or cat. It's, is there a man or we can have all 4, right? If we've got a happy family, you can say, yes, it's a man and it's a woman and it's a dog and it's a cat. And I'm going to call it, instead of multi-class, I'm going to just call it multi-label. Yeah. Final layer.
So the final layer have like 4 nodes where the sum of them sums to 1.
So this summing to 1 is we're going to hit that in just a moment. Okay. Right now, so this is, let's say, the man, woman, dog, cat. Now, given, here's a picture, and we have a cat and a dog lying down. So how many of these do we want to fire? How many of these do we want to be high probability? All 4 of them. So these will all be sigmoid. Okay. If we wanted to say just 1, pick your best shot there, then we're going to want the sum to be equal to 1. And we'll see that in just a moment. Does the difference make sense? Yeah. Okay. So again, if we look, let's say, at the cat, what would this how would we be interpreting this output? Say that again. Well, no. So we might, when we're actually labeling our test data, decide that 0.5 is a good break-even point. But how do we interpret this? Just in general, what do we think the output of this neuron means?
Percentage chance
Yeah, or the probability that
a man is in the picture.
This is a cat, but that's fine. So probability cat, there exists a cat in picture, given Yeah, that image. Does that make sense? Okay. Softmax. Well, let's say we only wanted one of them to be true. So we don't have any pictures that include dogs and cats. We have this picture, someone jumping up in the air, I guess, and we have this picture and so on, and we want our best guess as to which class it is. So here, what do we want? In our output layer, we want 4 neurons. We want them to be outputting something in the range 0 to 1. It'll really going to be the open interval, not the closed interval, because none of ours can ever get us to 1. And we also want the sum to be equal to 1. So this is what we use, the softmax. Softmax. If we look at our training data, right? Let's say we look at this training data. So X equals this image. What's Y equal? Assuming this is man, woman, dog, cat. 1, 0, 0, 0. So this is a vector, 1, 0, 0, 0. Does that make sense? And this up here, the image is actually a vector of our pixels times our height times our width, right? So 1, 0, 0, 0. This is often called a one-hot encoding. I love the name of this. Just the one-hot, it seems very descriptive to me. So it's basically 1, 1 and a bunch of zeros at the right location to specify this. It's surprising how many one-hot encodings are used when you would think they would just provide a number. I'll give you an example. Let's say we were doing cards in a deck of cards. So how many are there? 52. So we could just provide a number from 1 to 52, where let's say 1 to 13 is clubs and 14 to 25 is diamonds and so on. But another thing we could do is we could just provide a 52 long vector. How many zeros? 51 with 1, 1. So we've got a one-hot vector, okay? I'm getting to where softmax comes from. So now let's say we do our prediction for this. All right, we predict this, and we get our y hat, which is our prediction, equals, well, it's not going to be 1, 0, 0, 0, is it? No. It's going to be, and let me just document this a second. So this is our prediction. And y is our actual label. So label, or target, or you might call it ground truth. All those things could be. So let's say this is pretty good. We have done a fairly good job of training it. So we have 0.9 and 0.07, and to the limits of what we can print, 0.0 and 0.03. Okay. So the soft maximum is sort of saying we're not pushing them into 1s and 0s. We actually have intermediate values here. This is kind of roughly 1, 0, 0, 0, right? It's just not exactly 1, 0, 0, 0. And when we look at the error for this particular example, we're going to use some sort of function to measure error, but we're going to be comparing 1 against 0.9, and 0 against 0.07, and 0 against 0, and 0 against 0.03. And would we want this to, in general, measure pretty good or not pretty good? It's not a lot of loss here. You know, we're close. Would we like to be closer to 1 than we are with 0.9? Yeah. So we're going to try and update the weights. So we push the 0.9 higher and the 0.07 and the 0.03 lower, and we leave that 0 alone because we love it. So if we look at the sum of the GI of x's for all i's in what, over what is this summation taken? Say it again. The neurons. The neurons where, though? In this case, the final layer. In general, Softmax could be used anywhere. It's almost always in the final layer, but it could be used anywhere. So this is for the eyes. So this is the neurons eye in a specific layer. We will shortly come up with some terminology so that we can easily talk about the fifth neuron in the third layer. Okay. For Softmax, by definition, every activation function in that layer has to be the same, right? I mean, otherwise, this summation just doesn't work. And in general, almost universally really, the activation function for each layer is the same. So it's all going to be ReLU, or it's all going to be Sigmoid, or it's all going to be Softmax, and so on. Questions? Oh, so we were saying that summation of the G of I of x's, that basically equals e to the, I'm going to subscript with I for the ith. Let's see. If we're coming in here, it's really simple to see that if we add it up, we just get the sum of the e to the ix's. And our denominator is going to be the same thing. So our total is going to be equal to 1. And actually, what's our range? Yeah. 0 to 1, right? Because e to the x is in what range? 0 to, yeah, non-negative. Maybe I'll even say positive. And then our sum is gonna cause us equal to 1. So we can't ever be bigger than 1. We can't ever be smaller than 0. Questions on the Softmax? So are you going to be using Softmax? Sometime. Well, actually, are you going to be using Softmax like in the next week in 1 day? Yes. You aren't going to explicitly be asking for it, but you're going to be getting a Softmax in your last layer. And how many neurons are there going to be in that last layer? 120, because there are 120 dog breeds. All right, so here's a representation of a neural network. And there's going to be a lot of notation. And I apologize for that in advance. So let me just describe a little bit of the notation. So in I equals the size of the ith layer. By size, what do I mean? Say that again. What's happening? So it's the number of neurons. And if we talk about the first layer, we're going to call that in to the bracket 0, right? That's going to be the number of inputs. So it's handy to have that same notation. So we have x1s through x. The last one is into the bracket 0. That one make sense? Okay, we have 2 arrows. I just didn't want to draw all the arrows, right? We have more dot, dot, dots. We're going to make this a fully connected layer so that we have a connection from every input to every neuron in layer 1. Some networks don't have full connections, but that's kind of the bread and butter, I guess, of neural networks would be fully connected layers. So what do we got at a particular neuron? Let's look here, zoom out on this neuron. So we've got W, and we've got B. B is a real number. W is a vector. So W, 1, 1 might be equal to 3, negative 5.2, 7. Make sense? Okay. How big is this array going to be? The size of the input. So we're going to be, this is a n to the 0 by 1. And let's look at x. Okay, assuming here we only have 3 inputs. X is going to look like some inputs. I don't know, 3. My random number generator seems to always start at 3. And the next number I was going to say was 52, so that's pretty bad. 39 and 6. All right, so it reminds me of the story from Bell Labs. So Bell Labs, how many people have heard of Bell Labs? Right. So it was, in some ways, the Google of its time, let's say, or, you know, nice place to work. So what people would do there is, so one guy would often make some sort of an argument, a statistical argument. And they didn't, right, random number generators were not so easy to come by in those days. And so they would just kind of, see how this works. He would come up with a random example and use that to convince the person next to him. Okay, but the person next to him would not be happy if he came up with the random example, right? He wanted some randomness to it. So what he would do is call and say, I'd like a random number, please. Okay? And then whoever was on the other end would give him the random number, and then he'd use that as his example. Okay? And it always worked. He was very good at it. It turns out what he did was he had 10 friends, and each of them knew, when I call you and ask you to give me a random number, give me the number, one of them would be 5, and one of them would be 52, and one of them would be 3. And so whatever random number he needed to make his example work, he'd call the right person. So, okay, so we look at a given neuron, and we're going to be computing the, let's call Z the weighted input. And let's call A the activation. And you will see Z and A are what are used for these. So we look at the particular neuron, we first compute the weighted input, and then we apply the activation function. So if we look at Z11, the subscript here in this 1 means the first input in its layer, and the superscript bracket 1 means the first layer, or layer 1. So this is going to equal, and we're going to do a matrix multiply. So we're going to take W transpose X plus B. Right, so that equals 3, negative 5.27 by 339.6. I really shouldn't have chosen large numbers like this, should I? Plus B, and let's say B is 3. So that equals about 9 plus negative 200 plus 42. So about negative 150 plus 3 is about negative 147. So negative 147 is Z, which is the weighted input. What do we have to do from there? We have to apply the activation function, and we haven't specified what that is. But we would have the same activation function for everything in layer 1. Everything in layer 2 would have the same activation function all the way to the output layer, which kind of just looking at it looks like it would be what kind of a activation? Yeah, looks like it'd be sigmoid. Does this part make sense so far, what we're doing? All right. So let's look at a simple example where we've got this. How many layers do we have? Well, yeah, I should say 1 hidden layer and then 1 output layer. Yeah.
So I can go with one slide.
I'd be happy to.
So there's the H1 below the first kind of circle. Yeah, so those H's, what are they?
We're going to call those the neurons,
Oh, okay.
just as a way to name the neurons.
Oh.
Okay. So Z1, 1 is equal to W1 to the 1 inverse, or transpose times X plus B, and then A is equal G applied to that. And then we can go through and say, okay, Z2, bracket 1, equals W2, and you correct me if I get this wrong. I got one wrong. I'll be right back. Unless I'm messing up a lot on the way. So let's say 2. So, which, right or left? What's your question? So we're trying to compute the activation for, first we're going to compute the weighted input for this neuron, right? And so we take W2, the weights for the second neuron at the first layer, transpose times X, right? Same X, right? Plus the bias for the second neuron, first layer. And then we go ahead and apply our activation function. And theoretically, this should be G sublayer, or super layer. So let's just, right? Because we're actually saying the activation function for that particular layer. And then, right, Z3. And you can see this gets kind of tedious. And it also makes for a lot of code that actually gets executed. Right, because basically what we do is we wouldn't write this out like this. We would write in a for loop, right? So we'd have kind of one for loop going down for every layer, and then another for loop going across layers. B3. All right, and let's skip Z4. And now let's look at our output. So here, what is it we're calculating? Z1, 2 equals W 1, 2 transpose X plus B 1, 2 and A1, 2 equals G of Z1, 2. Okay, could you program this? You could write your 2 nested for loops, except it's actually more than 2 nested for loops. Why is it more than 2? So with 2 nested for loops, given an input, we get the computed output, right? But how many inputs are we actually going to be working on? A lot. So we've got to out our for loop to work over all the instances of the training data. And so up until 5 years ago, 6 years ago, that's how it was done. I mean, you'd write your loops. You, of course, would not do it in Python because that'd be slow. You'd work in C++, let's say, and you'd code it out, and yeah, not that much fun. We had a, ugly is not quite the right word, but an intricate neural network example 4 years ago in the machine learning class. We had a small amount on neural nets, and it's like, okay, let's go compute the activations for this. And it's not fun code. Okay, so sadly, I could have just forwarded through this, but I forgot about that.
For like
Brandon.
the second layer, we still, yeah, so A1 square root of 2,
Uh-huh.
still consider the original inputs, or consider the weighted?
So no, we are,
I think of the last line.
oh my goodness, let's fix this. Good point. Thank you, thank you. This is not x here. What is this? So this is A11. Oh my goodness, thank you for pointing that out. Right? So now we're actually feeding the output of the hidden layer into the input of the output layer.
What about those weights like W1, 2?
Uh-huh.
How do they come about? Do you learn them?
We're going to learn them on Wednesday. Well, we're going to learn how to learn them on Wednesday.
Right.
So, yeah. Just sort of as a preview, what happens is we take a training, we initialize our weights randomly, okay? And think about why we can't just initialize them to 0. Okay? But we initialize them randomly. We take a training example, we look, and we see what it predicts. So we run forward through the network and come out with our y hat. We compare that to our y. It tells us how bad we are. And then, basically, we work backwards through the network, updating our weights based on that error. Okay? That's roughly what is happening. So that we're better for this training example. We don't really do it a single training example at a time. We do multiple training examples. But that's what happens. What if we had what if we had a linear activation function? Okay, so here, g of x equals, let's call it cx. And here, g of x equals, we'll make it different, dx. What would this compute? It's a linear, right? Our weighted input is a linear combination of our inputs, right? What's coming out of B1? Or sorry, coming out of H11? It's a linear combination of x1 and x2, right? Because we have, let's say, z1, 1 equals w1 x1 plus w2 x2 plus b times c equals c w1 x1 plus c w2 x2 plus cb, which is a linear combination of the input, right? So the output from the first hidden layer are 2 linear combinations of the inputs. And kind of by induction, everything from then on is going to be 2. And a linear combination of inputs is not a great thing because it's very limited in what you can learn. Okay? So that's why we have nonlinear activation functions. And that was really the key thing that reinvigorated neural nets, is having these nonlinear activation functions so it could learn interesting things. About 5 years ago, roughly, 5 or 6 years ago, some enterprising grad student, I'm not sure who it was, I should look that up, said, well, you know what? I have this, neat GPU rig that I have at home because I play whatever it would have been playing at that time. Dota, let's say, okay? And it's got all this fast matrix multiplication. Wouldn't it be neat if we could use that for, no, not Bitcoin mining, but deep learning? So here's the deal. We're going to take Z11, right? I'm just repeating what we had done before. What Z11 and Z12 and Z3 and Z4 are. Right there, okay? And I'm going to say, wouldn't it be nice if we could do this in one fell swoop, right? Rather than having to compute all 4 of these. I mean, it's 8 really, but order of the number of neurons we have. So what we're going to do is we are going to stack together our weights. All right, so we've got W, and this is capital W, at I equals, so let's look at this stack. And we're going to pre-transpose it. So what we're going to actually do is take W1 at I transpose. I'm not going to put the parens around to show the transpose. Just assume the transpose happens afterwards. So, and then W2 at I transpose all the way to W4, in this case, good, I transpose. Each of these, in turn, is actually, right, a bunch of weights. So what is the, I'm not going to make this 4. I'm going to go ahead and make this really what it should be, n to the what? Into the I, into the square bracket I, right? Because we have that many neurons. So what's the size of this matrix? So n to the square bracket I, right? Because that's a number of neurons. You could just put that number of neurons times number of inputs. And what is the input size? In our terminology, which makes everything perfectly clear. N to the square bracket I minus 1. Okay? Because the input to the one layer is the output of the previous layer. Okay, so we vectorized that. We got that done. Now what does B look like? B looks like B1 superscript 1 all the way down to Bn to the I superscript I, and this is an I. And so we're going to call this B at I. So its size, how many rows? Number of neurons by 1, so this is N at I by 1. So now what happens when we take W at I times X plus B at I? We're basically going to be taking this row times, I guess we need to look at X. X hasn't changed, right? And I guess let's assume this is the first layer for the moment, so that we are dealing with X. Okay, so we're going to multiply this row times the X column, and we're going to end up with what in the top here? First, what type? Is it a vector? Is it a real? Should be a real number, right? It's not quite an activation. It's a weighted input. We're not to the activation yet, right? So this is basically going to be Z1 at I. And the next one is going to be Z2 at I, all the way down to Z into the I at I. So this is going to be Z at I. And if we then apply G to it, what's that give us? Point-wise applying G, right? So for every element we're going to apply that. We're going to end up with A at I. Now, here's where GPUs really shine. Here. They're really good at this, and they're also pretty good at this too. But that WX plus B with giant matrices, it's really good at. Okay? Because it loads them all up into the GPU memory, and then does, what is it, SIMD, I guess? Single instruction, multiple data. So it's doing the same thing across all of them simultaneously. Yeah.
Can we
True.
do anything about the dimensions of
Ye-
the, like what would they be?
Well, yeah, we know that the dimensions of Z are going to be the number of neurons in layer I times 1. Right? Because it's going to match B. Yeah. Other questions about this? So can you see how this provides us some nice speed up? So how many loops are we going to have now?
Just one.
Well, we still have to do, so this is for I. Now we've got to do I plus 1 and I plus 2 until we get to the last layer. So we're going to have a for loop that iterates over the number of layers. Okay? Yeah, so for each layer we'll do this matrix multiply, we'll do this application of G, and then we'll go on to the next, and go on to the next, and go on to the next. Part of what we need to make sure of is a GPU can store all this, right? That it has enough memory to store all the weights we need plus our input and any intermediate values that it needs. All right. But wait, there's more. We're not operating a single training example at a time. We're working in batches. Right? We have 25,000 cat and dog images. Do we really want to go through them one single image at a time? No, let's group them together in batches of 100, let's say. And if we could take advantage of the GPU, boy, would that be great. So we have new terminology here. So this is the ith training example. The superscript. So let's see what we're going to do here. For I equals 1 to m, where m is the number of training examples. And I'm going to assume we have that simple network that we saw before, right? One hidden layer. So we're calculating Z 1I. That is, let's just read this. This is the activation for, is this the activation? What does Z mean? So it's the weighted input for first layer, the entire layer, right? Because it's a vector. For the paren I means ith training example, right? And that equals the big W weight, right? So this is all those weights for hidden layer 1 transposed. I take that back. There's no transpose here because I pre-transposed those. So there's no transpose. Times x at I, that is the ith training example, plus b. Apply the activation function. Do the same thing for layer 2, and now we get our value. And then here is going to be somewhere here is going to be update weights. But again, we get to that on Wednesday. Okay. So the fact we're doing the same thing and all we're really changing is this superscript gives us an idea we can do something to vectorize this. Right? And one way that this vectorization helps, right? In Python, you're much better off, instead of writing an explicit for loop to multiply matrices, to use NumPy. Right? So NumPy is great because then it'll go down to using C, and it's much quicker. But even better is to go down even lower, which is to go down using the CUDA library that runs on NVIDIA. Right? So if you're going to buy a GPU for playing games, might as well get an NVIDIA because then you could do machine learning. And that'll make it even much, much faster. So here's what we're going to make. We're going to make, yeah. Thank you. That's lowercase a. So we're going to define uppercase A in just a moment. So uppercase A and uppercase Z are going to be applied to multiple training examples. So we are going to create X. So this is capital X, and we're going to have X, the first training example, which is paren 1, X paren 2, all the way to X paren M. All right? Each X has a bunch of rows, right? We have our capital Z is going to be lowercase z1. Sorry, we don't have a lowercase there. We have a uppercase. So the first layer, the first training example, the second layer, hold on a second, just erase that. So our first layer is going to be Z, yes. Okay. We want to just be dealing with the first layer. And we want to be dealing with multiple training examples. So we have Z1, 2, Z1, 3, and so on up to Z1, M. Okay. So we're defining this. We haven't calculated it yet. We're just defining it. And then similarly our A vectors. So A1 equals lowercase a 1, 1, a 1, 2, all the way. All right, so what does our computation look like? We're going to basically say Z at 1 equals what? It's going to be on the order of WX plus B, right? I mean, it's roughly going to look like WX plus B. Can we just do W capital X plus B? So this is weights for layer 1 and biases for layer 1. Does that work? So our big weight example, let's try and remember this again. We had going across were the weights for neuron 1, the weights for neuron 2, the weights for neuron 3, and so on. And then we're going to be multiplying it by all these x's. So we're going to end up with, before we had z, right, so z1I was equal to something that looks like this. Number of neurons times 1. Yes? After our big Z at I equals how many rows? Same number of neurons times m, the number of training examples. So we can then calculate A at 1 as what? G of Z1. And then calculate Z at 2 equals, what weights do we want? W2 multiplied by A1 plus the biases for weight 2. And then that's all.
I get that we want to be able to compute things really quickly, but doesn't that come at the cost of our learning rates? Since we can only update the weights after we've done
So we actually, there are 3 various ways you can update learning. You can update. Okay, you can do the, I don't know if I'd say traditional, yeah, the old school, which is you run an entire epoch. That is, you do all of the training examples, and from that you can figure out your overall error. Right? You can know exactly in which direction that you want to go in order to update things to reduce the loss, because you've looked at every single training example. At the extreme other end of that is what's called online training, where a training example comes in and you go ahead and figure out its error and then update the weights based on that one. And if another comes in, do it for that. Another comes in, do it for that. In between, even without these updates, we do this batching and we get the stochastic gradient descent. So we take a random batch. We're going to iterate through our instances for each epoch differently every different time. So we're going to get a random batch and we're going to say, we hope this batch is big enough, we're kind of going in a good direction. It's possible this was a set of all particularly bad examples where we're going to go in the wrong direction. But when we get our new examples and keep going, it'll fix that up. So really this is good and what we want, both for speed and for the learning. So this is what is actually used in PyTorch and TensorFlow and so on. M is not going to be all of the training examples. M is going to really be whatever our batch size is. What might affect the batch size? Say it again. GPU, what about the GPU? And what prevents it from handling? What's the limiting factor? Space, right. So the amount of memory you have on your GPU is going to control your batch size. Well, that's not quite true, right? It's the combination of your neural network and how many weights it has, how many biases, in combination with your batch size. So if you have a simple network, you can have a much larger batch size. If you have a complicated network, which you'll find as we do this later on. So ResNet, we're using ResNet 50, I think in this example, ResNet 45. So that means there are 45 layers. There's a ResNet 90. If you do ResNet 90, you'll find you'll need to decrease your batch size or you're going to run out of GPU memory. So this is how the forward pass works. Wednesday we're going to talk about the backward pass. So actual learning will happen. Wait, I hope learning has been happening all these last few lectures as well. But learning will continue to happen and the actual neural network will also learn. What else are we going to know Wednesday? We're going to go through the Google Cloud and setting that up. All right. See you on Wednesday.